Thanks a lot for to the panel for the very interesting discussion, and thanks a lot, Ingolf, for moderating it. It's a pleasure for me to take over from my colleague Natalia and moderate the next 2 hours of the Quantum Summit 2022. So my name is Lukas Klingholz and I'm Head of Cloud and AI at Bitkom. And the next presentation is being presented by Dr. Christian Tutschku. He is team lead for quantum computing at the Fraunhofer Institute for Industrial Engineering, and he's presenting his view of quantum awareness to quantum readiness. And it's an application-based algorithm design and know-how transfer focused in his speech. So the floor is yours, the stage is yours. We are very interested in your considerations on these topics.
Yeah, thanks a lot for this kind introduction. It's a pleasure to give you a small insight in what we are doing at Fraunhofer in GADDEN companies, from the quantum awareness to the quantum readiness, and how it's currently, how we conduct application-based algorithm design, and especially transfer this know-how towards the German industry. So this talk will guide us here through this path, and I will start with obviously a short introduction. So what is quantum computing? I don't want to make it very detailed, but so far we had the CPUs, the GPUs, and they rely on transistors, amount of transistors and chips. They have grown exponentially, Moore's law. They have saturated. We need new power. And one ansatz to get new power is the kind of QPUs where we can not only simply calculate with 0 or 1, so current or voltage on or off, but with some kind of superposition, Schrödinger's cat, in a quantum computer, and that gives us a completely new paradigm. So, but the most important thing is that this whole paradigm of calculations is not deterministic, but it's probabilistic. So this is a very, very hard concept to grasp for current software engineers, for informatics. So that's why we need an interdisciplinary team to conduct the algorithm design. So it's a new kind of paradigm. And where are we currently, and why are we interested at an application-based research institution like Fraunhofer in quantum computing? So because it claims that we can, or at least this is what we also see, that we can solve algorithms which can be solved already good on a classical computer, but they are expected to solve it really way faster. So the real-time solutions, the exponential or up to exponential speed up in time, is one of the reasons why we can solve use cases like take into account traffic jams or something in a routing problem really just in time, and also making creating solutions which are currently untraceable by classical algorithms in future, make them traceable because of the reduction of the complexity. Quantum computing is green computing, so we have here a responsibility as well. We do not only solve use cases which are say in a kind green, but the computation scheme itself is green, since we cannot even simulate qubit systems more than 70 qubits. So and we hope, or we see, that we get a higher accuracy already with a few qubits, because we have a way larger Hilbert space, configuration space, which we can search through to get better performing solutions. Yeah, but all of this are now ingredients. But where can we find these ingredients? What are use cases we're currently tackling? So this goes through all of the branches. So there is no special branch which is just reasonable for quantum computing. You can find it everywhere. Distributions or combinatorial optimization problems, like, for example, distribution and control of charging stations, hydrogen pipelines, but also in the logistics sector, the route planning for trucks, or the predictive maintenance and routing problems, or in the production, so the job shop scheduling problems and the optimization of scheduling routines is one of the big application areas we're currently looking at, as well as the finance sector with the portfolio analysis and the risk model valuation. And in the engineering parts, we mostly look at CFD calculations, so computational fluid dynamics, which can be tackled with quantum computing due to the fact that we can solve inherently good linear systems. And also obviously in the security area with Shor's algorithm to decrypt RSA decryption, but also on the quantum key distribution and so on for the communication scheme. So there are all kind of branches included, which we currently tackle here in the German industry. And when I say we do not do this as one institute here, like the IAO, but the whole Fraunhofer Association clustered in, say, 7 competence centers all over Germany with a different focus on hardware and software. And yeah, with have access to the first, say, quantum computer in Europe, or at least in Germany, which is GDPR compliant, which is extremely important for our industry users. Since obviously we want to process here confidential data and they should go through an all German pipeline. So yeah, and when I say, okay, we have this GDPR compliant backend, what are we actually doing within this competence cluster here? We conduct all of the hardware software co-design. So there are institutes which more go to the qubit design, to the control and readout measurement, like optical systems, for example, at the IOF in Dresden, or really tackling the hardware, the software stack, going from the algorithm design up to the applications and building the companies or the enterprise network to make them quantum aware, to make them quantum ready. So there's all the way from the hardware software co-design is tackled within this competence network to serve as a local contact point for the industry. And so we, as a Fraunhofer IO, are conducting the Competence Center in Baden-Württemberg. And I will now exemplarily show you how we are doing this, what's our ansatz here, what's the module for getting the industry quantum ready. So here you see some of the projects, which are more hardware-based, so simulating NV centers, for example, at the Fraunhofer IAF, to pilot project, make Quava algorithms for optimization on the back end, so for combinatorial optimization problems, more reliable, studying error mitigation techniques, really application near algorithms like Sequoia, which is a project for hybrid quantum software engineering, where we build up an enterprise network of about 30 enterprises, from small one to big one, looking at their use cases from the areas I mentioned above. And also the AutoQML project, which is a project for automated quantum machine learning to really serve as a contact point to industry, to not need the usage or the expertise of a quantum developer to make automation, like it was done for the AutoML case for the KAI, now with the quantum aspect as well, to serve here to offer here quantum machine learning and algorithms for certain use cases automatically. And our ansatz is really to have the industry very close to the research partners. So within here, the competence network, there are all of Fraunhofer partners and universities, R&D partners, very close to the industry network, which we built up here over all the branches, and they bring in their use cases from all the sectors, and we are here experts obviously in the optimization, so in the algorithm part, so optimization, AI algorithm, the numerics for, let's say, the CFD calculation or the material simulations. And this forms here this kind of quantum advantage, where we are close to the backend, which we then in the end use to calculate, and also have our, for example, at the HLRS at the University of Stuttgart, an HPC system to simulate everything. And what we are doing here is we create the low-level NISQ programs, so programs which already run in the noisy intermediate scale, and create high-level tools here to make it accessible to developers in the development departments of the industry. Then we study best practices also in the quantum software engineering part, and develop these demonstrators which run then as application on the backends. One of the most important things is that we also, as it was mentioned, I guess, during this day a lot of times, we create this network of enterprises together with the research parts, and qualify and transfer. The technology transfer is one of the main aspects. And the transfer here is not only within the Fraunhofer community and the universities, it's all over Germany. There are big associations which support us here. All our results, for example, go to the Planck universe for quantum supported artificial intelligence, and we also support here to the AutoML framework, for example, the quantum solutions. So, and how do we tackle now these use cases from the industry? This is now just a model that you have a small intuition how to technology transfer takes place, more or less, how to model these use cases. So in the NISQ era, you can't tackle very, very large problems currently. So everything needs to be reduced to a kind of principle, proof of principle or minimal model. Like it's, for example, if you want to solve an N-cross and Sudoku, just solve a 2x2 Sudoku. If you can do this, you can do mostly everything if the hardware scales them. And yeah, for this, we develop algorithms like a Grover algorithm, which searches, for example, the optimal solution for this kind of Sudoku. Then we implement this on the backend, more or less, transpile it to the backend, and then run it. And then we see that with the highest probability, you get out the correct solution of this small proof of principle. So in a sense, this is abstract, but exactly this happens for all of the use cases the industry hands over to us. Construct the minimal model, set up the algorithm, run it, and then make it reliable because it's a probabilistic calculation. And as an example, for example, I brought one example from Llama project, which is Laden am Arbeitsplatz. You have a certain configuration of a charging column infrastructure, and you want to optimize the workload here. And you want to optimize it in the sense to economical aspects, make it cheaper, to ecological aspects, use better sources for the energy, and the technical aspects as well. And the main problem here is you have a certain charging plan with certain peaks. Peaks are expensive. Peaks are bad for the economy because you need to have bad sources of energy. If you can reduce them, that's an extremely nice thing to do also from the green computing side. But this task is currently way too hard for the quantum computer. It's too big. It's just too big. So in the first step, we need to model the system, and we need to model it such that it looks like this. And in the end, you have discrete versions of these charging plans with two cars, blue and orange. And then you just play an combinatorial optimization. You play Tetris with the quantum computer where it's really powerful, one part where it's really powerful, and then you can reduce these kind of peaks. And so this is abstract. What happens is in the end that you formulate here, that's a bit complicated maybe, but you formulate your problem into a kind of cost function, which dictates to the amount of costs of your charging plan. And this you need then, so this comes mostly from the industry, and this we then take to a minimal model and translate it to something the quantum computer understands, which is here a kind of so-called Ising model. And this Ising model this Ising Hamiltonian, which encodes exactly the charging plan, can be minimized by starting with a Schrödinger's cat, everything in complete superposition. So every solution is within this kind of computational state. And then you design an algorithm here, which is not mandatory to understand now, but what it does is it's designed on the Fraunhofer side currently, and it reduces the costs such that in the end, with the highest probability, the best charging plan is the outcome of our calculation. Yeah, and this is how it looks like. So we take the problem from the industry, we design the algorithm, we map it. So then it looks like this more or less. We map it to the topology. So these are the set 27 qubits on the inning and backend. And then, yeah, we run the algorithm to solve the problem, always really close and in collaboration with the developers to not lose the abstraction levels and the hardness or the caveats, the bottlenecks of the classical algorithms. Yeah, and coming now from the algorithm design to the transfer. So as a Fraunhofer association, we have within the Fraunhofer Academy, we have several programs to educate, to transfer the knowledge, not only in the projects we're conducting with the industry, but also as a Fraunhofer association as kind of education programs. And one of the education program is an free of charge a program with self-learning content where everybody can access to. Here you see the registration link. This is kind of online already, and it's for everybody who wants to get in touch with quantum, become a bit of aware and what can quantum really achieve, why is it good. So this is one kind which is already online, which is free of charge. Then, so this year started already in Baden-Württemberg, so the largest education program with more than 20 dates within this year. It's an annual program in a bi-weekly frequency. And so here we educate the industry really from the very basics of quantum mechanics, linear algebra, and Python, Qiskit, really to the algorithms and how to implement the use cases. So this is an overwhelming program, which is not free of charge. It's charged, but this serves then really as a big program, getting the knowledge transfer from the research to the application and to the industries. And beside this big program, which just has started, there are two more programs. One is a special program for security driven by the Fraunhofer ISAC. And you can also book this to get more in touch of the, for example, for Shor's algorithm, RSA decryption, how to get into this area of the post-quantum cryptography as one of the special issues, which is also here provided over the ISAC, but over the Fraunhofer Academy. And last but not least, we have also, starting in autumn, then a certain certification program conducted by the Fraunhofer IDWM, and the focus, giving you the technology transfer or certifying kind of quantum technology professionals for the technology understanding to become aware, and then also getting specialized mostly in the QML parts. But the certification, the goal is also to use, for example, things which we as IAO and IAF conduct in Baden-Württemberg to make all of the programs you become in the end then a Fraunhofer certified quantum developer, which is the big vision of the technology transfer within the Fraunhofer community. Yeah, and with this, I thanks a lot for the attention. Here are the three contacts. So for all of the competence activities or competence center activities in Baden-Württemberg, I'm the right person to contact. Dr. Hannah Wenzel is head of the competence network of the entire Fraunhofer Association here, and Raffaela Schätz is at least the program management for the Fraunhofer Academy. And as a last point, let me state that if you want to do something in quantum, no matter if you're a researcher, if you're a student, please feel free to contact us, obviously, because I think in all of our projects, we are more than happy to welcome you. Thanks a lot.
Thanks a lot, Mr. Tutschku.